So here is assignment 2-1. Now, a lot of the questions in this assignment is going to be similar to what we did last week or whenever you did it on limits. So that introduction to calculus, that whole unit and stuff that we did, that was a good introduction to limits. These questions, on the whole, will likely be a little bit stronger level, closer to an AP level that you need to. So you have the foundation now to be able to handle limits, to be able to handle derivatives when they come up. So let's work and practice this together. The best that you can do always is that you just don't follow the video and copy, but you first follow along in the video, especially, of course, if you don't know what you're doing. And then as you are getting strength, as you're getting stronger, the only way you learn something is by practicing it independently and knowing you're doing it correctly, and then going through that cycle again and again. So we need to practice, we need to get independent, and you need to know you're doing it correctly. All right, so here's number one. We're going to evaluate these limits, no graphing or table. We're going to do this using algebra if we can. So step number one always is, can you substitute in to evaluate the limit? So I'm going to plug 1 in to evaluate this limit. Now when I plug 1 in, I do get 0 over 0, but I'm not going to write that down. If you like, you can write down the word indeterminate, because that's what it is. And so we're going to solve and evaluate this limit by factoring. We need to divide out the 0 to be able to find what the limit is. So x squared subtract 1 is a difference of squares, so we're going to factor that out. X plus 1, x subtract 1. The denominator stays what it is, it's prime. And notice that x subtract 1 divides out. Now we can substitute 1 in and get our answer. So 1 plus 1, to evaluate that limit, the answer is 2. The next one, the limit as x approaches negative 1. 2x squared subtract x subtract 3. Step 1 always is to substitute in. So take your time, but plug negative 1 in. Make sure that's 0. Plug negative 1 in, that's pretty sure that's obviously 0. So this is indeterminate again. So to evaluate the limit, we're going to factor and divide out the whole. So because negative 1 is a 0 on top, I have this, that I know that x plus 1 must be a factor. That's that connection between a 0 and a factor. They're opposites. I'm going to use that fact to help me. So I know they're going to divide out. Then, when I look at the numerator, I'm going to then make it easier to factor this. So x times what is 2x squared? That's 2x. Negative 3, 1 times what is negative 3? So it must be 2x and negative 3. Make sure it fits. So first and last, so 1 times 2x and x times negative 3x, that they combine to negative x. So it does fit. X plus 1 divides out. Now you can plug negative 1 in, and you get negative 2, take away 3, and you get negative 5. 3, the limit as x approaches negative 1 of x squared subtract 1 over x minus 1. So here's that good example again, that step 1 is to evaluate, you substitute in. Notice when you substitute negative 1 in, your answer is not indeterminate. In fact, when I plug negative 1 in, the numerator is 1 take away 1, which is 0, and the denominator is negative 2. So 0 divided by negative 2, the answer is 0. By the way, 0 on top, good. 0 on the bottom, bad. That's what makes it undefined. Number 4. The limit as x approaches negative 1. And this is x cubed plus 1 over x plus 1. So when I plug negative 1 in, it's indeterminate, so there is a hole at x plus 1. This is called a sum of cubes. There is a formula to factor out a sum of cubes. What I'm going to do is recognize that negative 1 is a 0. So on the side, I'm going to use synthetic division because I don't remember the formula. There's 1x cubed, 0x squared, 0x, and 1. And then I'm going to drop the 1 down, and negative 1 times 1. We're just going to do synthetic division, which means I'm going to add and multiply as I go across. Negative 1 times negative 1, of course, is positive 1. and then negative 1. That gives me a remainder of 0. So what I'm left with here is allows me to factor it. So negative 1 is x plus 1 as a factor. My answer there is 1x squared minus 1x plus 1. That's what those are, coefficients for the answer, the quotient. And then we have an x plus 1 in the denominator. Notice x plus 1 is going to divide out, and then we're going to plug negative 1 in. So if I plug negative 1 in, I get 1 plus 1 plus 1. So this limit is approaching 3. Number 5. The limit as x approaches 5 from the right. Now, I want you to notice that if you plug in 5, that you get the answer indeterminate. So if you plug in 5, it's 0 over 0. Now, even though it says from the right, that's that little plus sign, I can still factor this. That's a difference of squares, and there's a hole there. Now, in this situation, when you plug in 5, you're going to get the same answer from the right or from the left. Now, what I'm left with in the numerator is 1, and when I plug 5 into the denominator, I get 10. So it is 1/10. If I said 5 and had a little negative, it would be the same answer. There is no jump there. There is no asymptote there. At positive 5, there's a hole. And so the right and left are both approaching the same hole, the same y-coordinate, even though when you get there, it's undefined. All right, I'm going to turn this page over. Number 6. The limit as x approaches negative 5. Almost the same question, but we're using a different x value that it's approaching. So this time it's approaching negative 5. So we're going to start it the exact same way. We're going to factor and simplify. So it's a difference of squares, so I write that out. Notice x subtract 5 divides out. Now, what happens now, and there's a 1 left over when you do that, when I plug negative 5 in now, this is not indeterminate. We have a 1, not a 0. So it's 1 over 0. That means this limit does not exist. So because it's a number not 0 over 0, that means it does not exist. Number 7. The difference of squares, x plus 2, x subtract 2. So right away I just factored out the denominator, so I wasn't messing around. I know if I plug in positive 2, it gives me the answer 0 over 0. Notice here we have what are called opposite factors again. So these divide out, but they're opposite factors. So it gives me negative 1 instead of positive 1. Now plug in 2 and you get the answer negative a quarter. Number 8. The limit as x approaches 3. By the way, anytime now you can do it yourself. That's how we're going to learn this. So right away I'm going to factor. So x squared subtract 9. That's a difference of squares. The denominator, that's negative 3. And I could write it as x minus 3 squared factored out, but it's negative 3 and negative 3 that factors it. I'm going to expand it that way instead of squared because then you can see what removes. Now, one factor only removes one factor. It doesn't remove both of them, just one for one. So now when I plug in 3, I want you to notice that this still does not exist because we have 6 divided by 0. That's undefined. That's an asymptote. And the limit doesn't exist there at that asymptote. Number 9. So again, try it. Write it down. As I'm doing this, I am writing down the start of the solution as I'm writing it down. So here I have 1. I notice x squared subtract 4. So that's a difference of squares. That's x plus 2, x minus 2. And in this case, without using a calculator, how would I find it? So I know exactly at positive 2, if I plug in, what's going to happen is it's going to be undefined. It's going to be 1 over 0. There's an asymptote there. The question is, from the left, what the answer is. Now, the good news is, because it's an asymptote, from the left or from the right, it's either going to infinity or negative infinity. So one answer, because it's an asymptote, still does not exist. That is still a good answer. The other answer it could be, to understand it, is if I graph this. And I know it's been such a long time to be able to graph this, but I want you to understand that if you graph this and had a little sketch of a graph. So at positive 2 and at negative 2 are asymptotes. All I care about is this part here on the right. I know that the bottom is more powerful. So the end behavior here is 0 on both sides. It's just a matter is it above or below? So when I plug in a number bigger than 2, like positive 3, I get a positive answer. This part is above. It's going to look just like this. At a vertical asymptote, it's either going to go to positive infinity or negative infinity. As soon as I know it's positive answer, it's going to positive infinity. I know the end behavior goes to 0 because the bottom is more powerful. The other thing I notice is that asymptotes can be even or odd. And if you look at the exponent here, because it's an odd exponent, that means one end goes up forever and the other end must then go down forever if I was matching this. So there's also another part to this and to the left, but this is the only part I'm looking at. So from the left, the other answer that you could write down is negative infinity. Number 10, a little bit more challenging, right? Without a calculator, without using Desmos. Number 10, the limit as x approaches 1, x over x squared plus 1, now, if I plug positive 1 in, you can get an answer. So why not just do that? So plug 1 in, and you get 1 over 2, which is 1/2. Done. So that's the best scenario, right? Where you can just plug in and get an answer. It's when something is indeterminate that you have to do some extra work. Or if it's a one-sided limit, you need to understand what makes it, what's happening at the one-side limit. Number 11. The limit as x approaches 4, it's root x subtract 2 over x subtract 4. And it says x is approaching 4. Step 1, when you plug in 4, notice it's indeterminate. We're not factoring here because you couldn't factor it anyways. So the radical sign, the square root, gives me what direction to be able to evaluate the limit. We're going to use the conjugate, which is root x plus 2. Root x plus 2. Now, we're going to keep the limit notation. And the numerator, we're going to go root x times root x is x, and negative 2 times 2 is negative 4. The denominator, we're going to just keep them beside each other and recognize that x minus 4, that whole, divides out. What you don't see is that 1 that's left over. Plug in 4, you get the square root of 4, 2 plus 2, and you get the answer, is it negative? No, positive 1. So positive 1 over 4. Number 12. Again, you're welcome to work with me until you have the confidence to be able to do it on your own. So limit of x as it approaches 3 of x subtract 3 root x plus 1 subtract 2. So again, step 1 is to plug in 3. Don't assume it's indeterminate because there are some answers here that you just plug in and get your answer. So plug in 3, it's 0. Plug in 3, it's 0. So it is indeterminate. So we're going to take that root x plus 1 and we're going to go plus 2. So root x plus 1 plus 2, top and bottom. Write the limit notation. Make sure that you keep writing limit until the very last step. What's the limit as x approaches 3 of this? The numerator, I'm just going to put beside each other. The denominator, first times first, is root x plus 1, root x plus 1. That's just x plus 1. Then negative 2 times 2. And I want you to know that when you simplify the denominator, 1 take away 4 is negative 3. So these remove each other. So they're removed. And then substitute in 3 for your answer. So that answer altogether is 4. All right, number 13. The limit as x approaches 0 from the left of root x, the absolute value, of x over x. So if I substitute in, it's indeterminate, which means it might exist or may not exist. But if I have a left-handed and right-handed, I really have to think through, especially maybe a graph that would help us here. So I'm going to draw a little graph underneath of what's happening. So these are finding limits without calculators. So if you didn't have a calculator, how would you evaluate this limit? So what does the graph look like? It kind of looks awkward. So I'm going to do a little table of values in my head to get a sense of what the graph is doing. So if I put in positive 1 or positive 2 or positive 3, I'm getting the same answer every time. It's 1. In fact, any number divided by itself is 1. But when I get to 0, I get no answer because it's 0 over 0. So I can't evaluate it, so I put a hole there. But any positive number that I plug in will always give you the answer 1. Now, how about for a negative number, like negative 1 divided by? So the absolute value of negative 1 is positive 1 divided by negative. And what you're going to notice is negative 1 gives you the answer negative 1 because of the absolute value bars. Negative 2, negative 3, they all give you a negative 1 as an answer. So any negative number then divided by itself because of the absolute value sign gives you a negative answer unless it's 0, and that 0 again is a whole. So there's a graph here of that function. Now from the left, what's the y coordinate? So from the left you can see the y coordinate is negative 1. If it had a little plus sign, then the y coordinate would be positive 1. And if it said not a plus, not a minus, if it was a two-sided limit, then it would not exist at 0 because at 0 there's a jump. So from the left, as x approaches 0 from the left, what's the y coordinate? And the answer is negative 1. Okay, let's look at number 14. Number 14 is the same, so I'm not going to graph it over again. So the number 14, the limit as x approaches 0. Again, the absolute value of x divided by x, exact same function. This time it's just 0. It's a two-sided limit. And with a two-sided limit, it does not exist. Why does it not exist? Because the right y coordinate and the left y coordinate, as they approach 0. So as you approach 0 from the right and 0 from the left, they don't agree. One answer is negative 1 and the other is positive 1. Because they don't agree, the limit does not exist. Mean girls. All right, number 15. The limit as x approaches 3 from the right. Now, these cute little double bars are what's called a greatest integer function. That's like a step function. So I'm going to remind you what that step function looks like. So those that did some of the work during the quarantine, they went through a lesson about parent functions where this is one of the parent functions we talked about. I'm going to graph it so we have an understanding of what it looks like. And I want to graph it around 3 so I know what's happening around 3. So a greatest integer function means the greatest integer less than or equal to whatever you plug in. So for instance, if I plug in 0, negative 1. Well, 0, negative 1, that's a point. And if I plug in any number between 0 and 1, so if I plug in a half or if I plug in a quarter, I'm going to get an answer where I go, what's the greatest integer less than or equal to it? It's going to give me negative 1. It's going to create a step at negative 1. And then at the next integer is going to be a whole, and then it pops up to the next step. So when I plug in 1, the answer is 0. And then again, it gives me that whole, that step. We'll go up here. So I'm going to keep following that step function. So we have 0, 1, 2. Here's 3. So when I plug in 3, the answer is 2. Now, 3 from the right gives me the answer 2. So I just plug in. Now, if I do the same question, let's see what it has. So the same question from the left, so that's number 16. So the limit as x approaches 3 from the left, oops, not negative 1, just negative. This greatest double bar, greatest integer function. So I already graphed it. So here we are, 1, 2, 3. Here's 3. So as you're approaching it from the right compared to the left, see there's a jump there? So it is a one-sided limit at that jump. From the left, the y-coordinate is positive 1. From the right, the y-coordinate is positive 2. Number 17. The exact same one again, but this time it is a two-sided limit. So we have x minus 1, two-sided limit. So notice at positive 3, because there's a jump at positive 3 of that step function, the limit does not exist. So the right limit is 2. And when you see it again, if you just plug in, you'd get the answer you're looking for, unless it's not an integer. Then on the left, it would be one step down in terms of how the steps work. And then when you go right at an integer, because there's the jump, the one side limit exists here. All right, number 18. So here we go again. So we're going to use that fact I just told you. So we have x plus 6. This is a step function. So at every integer, there's a step up in this case. So if I plug in 2, I get an answer that's an integer. Now the problem is at every integer, there's a jump. And because at every integer, there's a jump, this limit does not exist. So if I graphed it, there'd be a jump at every integer. And so what's the limit as it approaches that integer? It doesn't exist. It only exists as a one-sided limit because of those steps. These are the more challenging limit questions, right? Especially if you weren't able to do the work on step functions or the greatest integer functions before. But we're going to learn some stuff now. Limit as x approaches 3. Now I want you to notice this one, that when you plug in 3, you get the answer. So if I plug 3 in, I get the answer 3 over 2 or 1.5, not an integer. So it's actually in the middle of a step. So what's the greatest integer? So in other words, this is the answer, but I need to know what that means. What's the greatest integer greater than, or what's the greatest integer less than or equal to 3 over 2? So because 3 over 2 is 1.5, what's the greatest integer less than or equal to 1.5? And the answer is 1. Now, 3 over 2 is in the middle of a step. It only jumps at every integer. So at 1.5, it didn't jump. Number 20. Last of these. I know they're a little bit challenging, but that's okay. We're going to get through it and keep practicing. So this one is a one-sided limit. So the first thing I look for these greatest integer, these step functions, is if I plug in 5, is the answer an integer? Because I know at every answer that is an integer, there's a jump. So there is a jump here. So there's only a one-sided limit that exists. So I'm going to use my knowledge of step functions to help me. If I just plug in 5, that's going to be the answer from the right. So 2 times 5 is 10, take away 3. That answer is 7. That's from the right. From the left is one step down. And one step down from 7, the next integer, because it's an integer function like that, is 6. So when I plug in 5, the answer was 2 times 5, which is 10. Take away 3 is 7. So from the right, the answer is 7. So if I just gave a snapshot of this picture, from the right, you have a step there. Right here is what's happening at 5. There's a jump at 5. So if I plug in 5, the answer is what it says, 7. That would be from the right side. So when I plug in, the answer I get, that's right. Then you subtract 1. The next integer down gives me the answer to the left. So from the right, the answer would have been 7. The left, the answer 6, which is what I'm looking for. If there was no plus or minus, a two-sided limit, the answer just would be does not exist. All right, 21. These are piecewise. So the limit as x approaches 3, and I have 1/2 x plus 1. I have 12 minus 2x divided by 3. And then I'm looking carefully at the restriction. So notice the limit is as x approaches 3. At positive 3 is when it breaks into a second function. That's where the two pieces come together or break into two different pieces. I need to know that if this limit exists, that means when I substitute into the top, so I'm going to separate it into two limits. So if I plug this into the top, that 3, what answer do I get? So it's 1.5 plus 1, so that answer is 2.5. If I do the same work and plug it into the bottom, so if I plug it into the bottom, I get 12, take away 6, which is 6, and then 6 divided by 3, which is 2. Do these agree with each other? Does the right side agree with the left side? Are they the exact same answer? The answer is no. Therefore, this limit does not exist. So at 3, there's a jump of 0.5. If it had a little plus sign, the answer would have been 2. If there was a little negative, the answer would have been 2.5. But for a two-sided limit, it does not exist because there's a jump there. All right, 22. The limit as x approaches 1 of x squared plus 1, where x is less than 1, and x cubed plus 1, where x is greater than or equal to 1. And I want to know that limit and if it exists. So first thing I look at is make sure these are matching. Because if it said the limit as x approaches 2, you would just plug it into the piece where 2 is valid, which is the bottom piece, and you'd be done. But because we're taking that number 1 where it breaks into two pieces, we need to look at both. So for this one, I'm going to look at the top limit. So if I take the top limit only, so plug in 1, the answer is 2. If I look at the bottom limit by itself, 1 plus 1 again, because 1 cubed is 1, plus 1 is 2. They agree what the answer is. So because it agrees, the right and left agree, the answer is there, 2, and it exists. If there was a little minus sign or a little plus sign, the answer would still be 2. All right, 23. Here's the one I was talking about where we have to be careful. So the limit as x approaches 2, and then we have two pieces, x subtract 2 and x plus 2. Why we have to be careful here is that these don't match. If it said the limit as x approaches 0, I would need both pieces because at 0 it breaks into two pieces. For this one though, I only need to plug it into the piece that's valid. So in other words, this means the same as the limit as x approaches 2. When is 2 valid? Look at the restriction. So for the first piece, it's when x is less than or equal to 0. 2 is not that. The second piece is when x is bigger than 0. So when x is bigger than 0, it's just this bottom piece. And that's what 2 is. Since 2 is bigger than 0, I only have to look at the bottom piece. That's x plus 2. Then you plug in, and you can evaluate the limit, and the answer is 4. So be careful here to know, are you really looking at both pieces? Or is it approaching a number that only belongs to one of the pieces? So when x is bigger than 0, it only belongs to the bottom piece. If this number was -1 or -10, I would have only looked at the top piece. If this said as x is approaching 0, I would have to look at both. 24. These are going to be some calculator questions. So I'm going to flip over to Desmos to do these. So I'll write down the question first. 24a, the limit as x approaches 1, and it's sine x over 6x. Now I'm going to tell you that Desmos does not have a limit button on it, where you could just type it in and it will give you the answer. Our calculus calculator does have a limit button, if you have Nspire, then I think you should press the menu button, go to Calculus, and then from Calculus, click on Limit, and then you can type it in. But I don't have that. I could show you on the calculator in terms of that. Where is it? So this is what it would look like on an Nspire. Maybe I'll just show it to you on this video anyways. So if I wanted to evaluate a limit, I can go to Menu, and then go to Calculus, and then go to Limit. And then I would just type it in. As x approaches 1. Now this is if you had a little plus sign or minus sign, which we don't, so we leave it blank. It's not a one-side limit. And then in this, you press the trig button. So on the beside the equal sign is the trig button. So go trig and sign, and it's just x, and then I go control divide for a fraction. So I press control and then divide, and then in the denominator is 6x. Again, know that x is different than the times, not times, but x. Then I got to make sure, notice in the top right, my calculator says radians. If it's not in radians, I got to change the setting so it says radians. But it says radians. Control Enter, and it gives you the answer, which is 0.140. Now, on Desmos, here on Desmos, notice you would just type it in. I already typed it in. Because it's a continuous function there, it's only not continuous at 0. So even though it looks like it's continuous at 0, there's actually a hole there. If you went like, do you see the hole that's right there? So at 0, there's a hole. But at positive 1, there isn't. So you could actually just type it in and then go, okay, what is it at 1? And you get the answer. Same answer I just came up with. Now, for number 25, part B, I'm sorry, we have the limit as x is approaching 0 instead of 1. So as you see the graph that we had, notice again at 0 that we had, right at 0 there's a hole. Now does the limit exist when there's a hole? Yes, right? The left and the right are both approaching the same y coordinate. So if I looked off the graph, I could think it's 0.167, 0.16, that's what I would guess. 0.167, just looking off the graph in Desmos. If I use my calculator, I could come back here and I would just go back here, go back and highlight it, press enter, and then just change the 1 to a 0, and then go control enter. And then remember I said it was 0.167? Look at that, right? There's the exact answer. So 0.167 is a great answer. And I got it with Desmos off the graph and estimating it. Number 25, what's the limit? And this is a very lengthy one to type in. The limit of x approaches negative 2 of x cubed plus 2x squared minus x minus 2, x cubed plus 2x squared plus x plus 2. I just want to use my calculator. So if I'd use the calculator that you're going to get for calculus, this is what it would look like. I would press menu, calculus, and limit. I would type this in. So it says x approaches negative 2. And then inside the limit, I do a fraction line. So control divide, start with the fraction line. Then type in x cubed plus 2x squared, subtract x, subtract 2. The denominator, just make sure you typed it in correctly, x cubed plus 2x squared plus x plus 2, and then control enter, and you get the answer 0.6. If I would type that into Desmos, because there's no limit notation to use, I would have to type it in and then look off the graph and kind of trace it or use a table to try to get as close as possible. I'm just going to use our calculus calculator, and you can follow as I type in. Now, for number 26, again, this is the This is the limit as x approaches 2 of the absolute value of 2 minus x, 25x, subtract 50. Now, what's happening at 2 is if I plug in 2, you can see it's 0 over 0. It's indeterminate. I want to know what my calculator says. So it won't say indeterminate. It would actually give you, if the limit exists, it will say it. If it doesn't, it'll say it. So let's just see what it says when I type it in. So menu and calculus, and then limit. And then I'm just going to type in as x approaches 2, and then get inside the parentheses. Control divide for the fraction line, and then absolute value. So do you want to find absolute value on here? Beside the number 9, there's a button there. So to the right of the number 9, I'm going to press it. And then it gives you a bunch of quick functions you could quickly go to. So the one I want to go to is this one, absolute value with the bars. And then I type in 2 subtract x. And then in the denominator is 25x subtract 50. And then control enter. And what it tells me is there's a jump there for this one. And so the calculator says undefined. I can say that it does not exist. So we start off no calculator. Then can you find the limit with a calculator? And again, Desmos doesn't have a limit button or a limit function. It does actually have derivative and integration, which we'll use in calculus, but it doesn't have a limit notation. So I use the calculus calculator, the Nspire that we're going to use. If I didn't have it on Desmos, I could trace the graph or look off the graph to see what the answer is too. All right, so this is part 1 of the assignment 2.1. And then we're going to do another video, and it's right here you can have access to. It's going to be part 2 of the assignment. I fully understand that this took a while and that you should probably take a little break, maybe even come back the next day, and then finish assignment 2.1. So don't overdo it. I'm going to try to break it into chunks so that it's not overwhelming, but you're still doing math as much as you can. All right, Mr. G Math over and out. I'm proud of you for doing your work, and until next time.